Since I know you missed these, here we go. Second one, well, first one really, except for you, Callan. Multiplying fractions. Okay, I should actually spell this out correctly. Multiplying fractions. So I want to start with a little bit of review. If we have a over b times c over d, that when we multiply fractions, we multiply across the numerator and across the denominator. So 2 over 3 times 5 is 10 over 3. Notice how I multiplied the numerators but not the denominators. I would not make that 10 over 15. 1/4 times 7/8 is 7/32. This should go back to times that you've learned stuff like this before. Let's do some more basic ones. If I have 6x over y cubed, and I multiply that by y squared over 15, now I have some things that I can cancel. I can either cancel before I multiply, or I can write this all out as 6y squared over 15y cubed. And then cancel, aka divide. The 6 and the 15 can become 2 and 5. The y squared and the y cubed can become y squared over y. And I'd end up with 2x over 5y. And we'll call that A, and I'll call this B, and the other ones can just be like random stuff. 6/9 times 36/11. Remember, we can actually cancel before we multiply and just make that 1 and 4, so that this becomes 24/11. I do not ever want you calling it cross-canceling. That is a stupid way to remember this, and it's not very helpful when it comes to cross-multiplying, which is something completely different. So please don't ever call it that. Okay. Let's kind of go with some basics here. We have the rule of exponents for a power of a quotient. Okay, I feel like sometimes when I say that I'm speaking a foreign language here. Exponents are the things you raise, powers are also the things you raise, and quotient means division. So if we have a power of a quotient, that's like saying this. Here's a quotient, a divided by m. Here's a power, or a divided by b, power to the m. That's the same thing as a to the m over b to the m. So something like, I know you like real examples, if I do 3/7 to the second power, that's the same thing as 9 over 49. Why? Because it's the same thing as 3 to the second over 7 to the second. This should also be somewhat reviewish for you. So I'm going to box that in, and let's kind of do a few more examples. Okay, wait, I did A and B. I'll call this C, and I'll go D. I know it's a little scattered. That's fine. X to the third, or x over 3 to the third power. And that just becomes x to the third over 3 to the third, which I can simplify as x to the third divided by 27, or x to the third over 27. Another last one before we get to this worksheet that you guys are looking at is 4y over z to the third power. That is the same as 4 to the third, y to the third over z to the third. And 4 to the third is 64. And I have y to the third over z to the third. Okay, one more, I lied. Let's go 3x over y to the fourth times, then I'm going to do 3y over 8x. Order of operations says we raise the powers first, so I have 3 to the fourth, x to the fourth, over y to the fourth, and I have times 3y over 8x. Well, if I look at 3 to the fourth times 3, I could actually combine that to be 3 to the fifth. Then let's look at the x's. X to the fourth over x gives me, let's draw a denominator bar. Let's just go x to the third on the top. Remember, that would cancel. Then I have y over y to the fourth, so that's a y to the third in the denominator, and I still have that 8 in the denominator. Finally, if I want to express 3 to the fifth as something better, I can say that that is 243. 3 to the fifth is the same as 81 times 3. And x to the third over 8y to the third. Okay, now we're going to switch over to the worksheet here. Oh, almost got that right. Wait, still want to keep these here. Okay, blow this up. And boom. Name me, period, now. Show all work. Oh, it's something we always do. But give a restriction on each variable and then simplify. So here's a little review of what we did before. But you'll notice as we keep flipping, the back side has some multiplication. So let's just warm up with a start. Factor first, then state restrictions, and then cancel. Okay, let's factor first. GCF in the numerator, I take out a 9a squared, and I end up with an a minus a 3. Denominator, I take out a 9a, and I end up with a 2a minus 3. Beautiful. Let's state restrictions. Whatever makes the denominator equal to 0. So if I look at this piece here, I would end up with 2a minus 3 cannot equal 0. 2a cannot equal 3. And a cannot equal 3 over 2. There's one restriction. If I look at this piece right here, ooh, I don't really care about the 9. I end up with a is not equal to 0. So those are my two restrictions. Now let's go ahead back to the problem and cancel. 9's go. The a squared over the a goes away. And I'm left with an a times an a minus 3 over a 2a minus 3. Think of the 2a minus 3 as being in its own parentheses, which helps you see that nothing more can cancel. So let's link all these. That's all my answer with restrictions. Number dos, GCF first. Grouping symbols, we're going to pull out a 3z, and I'm going to end up with a z squared minus a 3z plus a 2 over GCF first, and I'm going to pull out a 3, I'm going to end up with a z squared plus 3z minus 10. One question to ask, can I cancel the 3's right now? Answer is yes. That's not going to affect restrictions at all, so I might as well just do that and not have to write them again. Z, and then I'm going to end up with z minus 2 and z minus 1. Then the denominator is going to be a z plus 5 and a z minus 2. Before canceling, I'm going to state the restrictions off here. Restrictions come only from the denominator. They do not come from the numerator. So I end up with z is not equal to negative 5 or 2. Remember, it's really opposite sign with the denominator. Then I'm going to cancel. Z minus 2's go. Oops. And I'm left with a z times a z minus 1 over a z plus 5. I'm going to pause this and magically cross all the z's. Since some of you really liked cross z's, I don't really care. 3. Numerator, GCF first. There is none, so let's go ahead and factor that. Two binomials, 2n and an n. I'm going for 5, so I'm going to want to do 3 here and 1 there, plus, and that's going to FOIL. Okay, denominator, GCF first. Take out an n squared, and I end up with an n plus 1. There's no such thing as a double restriction, and when I look at the denominator, all I see is just an n cannot be equal to 0 or a negative 1. Then we cancel out the n plus 1s, and I end up with 2n plus 3 over n squared. Let's kind of group all that together. Finally, number 4, numerator, GCF first. I don't see one, so let's factor that as a, factor as a plus 2 and a minus 1. Denominator, GCF first, I can take out a 2, and I end up with 4 minus a squared. That's a difference of 2 squares, so let's take this one step further. Got a plus 2, a minus 1 over 2 times 2 minus a, and 2 plus a. State our restrictions before we cancel. I've got a cannot be equal to, if I look at the denominator, I have plus or minus 2. Then I can cancel. Now, 2 plus a and a plus 2 are actually identical. They're not opposites. They're just in a different order, but it's addition, so it doesn't matter. So my final is a minus 1 over 2 times 2 minus a, with these restrictions from up there. Let's flip it around to the back side. Simplify. Assume no denominator equals 0. Okay, when we see these instructions here, what that means is we do not have to state restrictions. That is saying that let's just assume that we don't have to. So, no restrictions needed. That's what those directions mean. No restrictions needed. Watch for the directions. Always watch for the directions. It's like a life skill or something. So I'm going to put parentheses around our factors because that n squared minus 9 and the n plus 3 look a little weird. And I'm going to factor n plus 3, n minus 3 times 6n squared r squared. I'm actually going to draw it all in the numerator, and then I'm going to put all this stuff in the denominator. 3n r to the third, and then another n plus 3 in parentheses. I know sometimes I've told you guys you can't group stuff in parentheses, but that's because it wasn't being multiplied. Here, that dot means it is being multiplied. And since the numerator and denominator of a fraction bar are their own grouping symbols, I can actually put all this inside grouping symbols that look a little bit more easy to draw than a little box like that. Parentheses. No restrictions needed, so we can cancel. The n plus 3s are gone. The n minus 3 has nowhere to go. The 3 and the 6 can go to become a 2. And the n squareds, I'm going to stop crossing stuff out because it's going to get messy. I'm just going to write the 2. Let's look at the n squares. I have an n squared on the top and an n on the bottom. So I'm going to make it an n on top. Let's draw a fraction bar. I have an r squared and an r cubed. So it's an r in the denominator. And then I'm finally left with an n minus 3 in the numerator. So I'm going to draw a smaller fraction bar and circle that. That's my final. Number 6. We have to factor every part of this. This is actually the first thing we really need to do. Factor this, factor this, factor this, factor this. Okay, well, the first one's already factored. So I'm going to write that as x plus y quantity squared. That's already factored. How do I know? Nothing's being added. I'm not talking about the x plus y. I'm talking about like that's x plus y times x plus y. So it's already factored. But the denominator is not. That's not completely factored. I could separate that into x plus y times x minus y times GCF on this one. I have an a times an x minus y. GCF on this one, I have an a times an x plus y. So how's this going to work? Well, the a's cancel. The x minus y's cancel. Ooh, why do those cancel? Well, because our fraction bar can be extended, leaving this with just multiplies everywhere, but it's still just multiplying. So, okay, let's do the... Ooh, I have an x plus y in the denominator. That can go away with that 2 there. But then I have another x plus y that can actually kill the whole thing. So we get that it's equal to... Okay, you got a choice. Are we going to say 0 or 1? Well, it's division. A number divided by itself is uno. Don't ever put 0. Unless you're adding a number to its opposite. But here you're dividing. Number 7. Let's factor every part. So factor this thing, a minus 4 and a plus dos. Let's factor this thing after drawing a fraction bar. That would be a minus 4 and a minus 1. Good. Let's factor this thing. That would be a 2 times an a plus 4. And let's factor this thing. That would be an a minus 3 and an a plus 2. Let's look at what's on the top and what's on the bottom and cancel things that are the same. A minus 4s go. A plus 2s go. That's it. Combine what you have left. We have a 2 times an a plus a 4 in the numerator, and we have an a minus 1 times an a minus 3 in the denominator. Let's make that a better fraction bar. Maybe even slide this stuff over. Okay, I know, Gino, I'm failing. There we go. Last one. A lot of factoring here. Don't freak out. Just take it one factor step at a time. Let's group that. And that's going to become 2 sets. So I have a 2x and an x and a 3 and a 3. And it should be a minus 6 plus 3. Denominator, I'm going to take out a greatest common factor. Now, if I take a 2 out of this, I'm going to end up with x squared minus 9. So I'm actually going to skip that straight over and say this is 2 times x minus 3 times x plus 3. Save yourself a little bit of time there. Times, group those together, and I have x plus 3 and x minus 2. Factor this thing, and I have 2x and an x. And I want to do a 2 here and a 3 there, so I have 4 and 3, minus 4 plus 3. And now we're going to cancel again, so let's look for anything that's similar. 2x plus 3, 2x plus 3. X minus 3, x minus 3. X minus 2, x minus 2. X plus 3, x plus 3. So all those factors canceled except for the 2 in the denominator. I'm left with a fraction bar and a 2 in the denominator. And since everything canceled, that's just a 1 in the numerator, and this is just 1/2. Oh, I have more. Okay, let's factor r minus p, r plus p. Oops. Denominator, factor by grouping. So let's take those two and let's take those two, and we get an r times an r plus 4 plus a p times an r plus 4. And I have a times p, this would be r plus, why do I keep writing p? R plus 4 and an r plus 5 over, this is going to be r and r, 3p and p, and I want to do a plus 3p but minus rp. Plus 3rp minus rp. Okay, that works. But this isn't fully factored yet, so I do have to take one more little annoying step and rewrite the entire thing with the highlighted part fully factored, because that's not fully factored yet. So we have r minus p, r plus p. I pull that denominator apart into r plus p times r plus 4. Rewrite the entire second part, r plus 4, r plus 5, over r plus 3p and r minus p. Look for things to cancel. The r plus 4s are gone. The r plus p's are gone. The r minus p's are gone. And that's it. So I'm left with r plus 5 over r plus 3p. Number 10, we've got some more factoring. The a plus 5 can't factor, but the denominator can factor as 1 minus 2a and 1 plus 2a. The 2a minus 1 cannot cancel, or cannot factor, because there's no greatest common factor. But then I'm left with a plus 5 and a minus 5. So look for things that can cancel. I'm going to put parentheses around the a plus 5 and cross it out with this a plus 5. I have 2a minus 1, and I have 1 minus 2a, so I'm going to cancel those. But since those are opposites, 1 minus 2a and 2a minus 1, I'm going to stick a very large noticeable negative out in front. Finally, let's merge what we have. I have a negative, let's just make it a negative 1 in the numerator, over 1 plus 2a and a minus 5. Number 11, if I factor this out, I get y plus 5 and y plus 2. If I factor the denominator out, I get a 2y, a y, and then I would want 5 here and 3 there to get me 13, plus and plus. Here, if I keep it the way it is, I would have 3 and 2, and then I'd want the 2y here and the y here, so it becomes plus 4 and minus 3. Then I have 2y greatest common factor, pull that out, and I get a y squared minus 4. I'm going to cheat now and erase the y squared minus 4 and make it a y plus 2 and a y minus 2. So now let's cancel what we have in common. Y plus 5's go. Y plus 2's go. 3 plus 2y and the 2y plus 3's go, because those are really the same thing. The 2 minus y and the y minus 2 become a negative 1 somewhere. I'll just put it right here. And that leaves me with a negative 1 over 2y. Number 12, factor that as b minus a and b plus a all over 12 times, then I pull out a 3 and I end up with a squared plus b squared, but that can't factor. The denominator, I get a squared minus b squared and a squared plus b squared. One more step, b minus a, b plus a over 12 times 3, parentheses, a squared plus b squared over. I did that because I have to factor that thing into a minus b and a plus b, and then I still have a squared plus b squared. Let's look for things to cancel. A squared plus b squareds go, a plus b's go, a minus b and b minus a are opposites, so those become negatives, negative 1 somewhere. The 3 and the 12 become a 1 and a 4. So if I clean up what I have left, I have a negative 1 over 4. Oh, is that it? Good night, everyone. Have a wonderful end of this message.